So now another scanning technology that you can use with uh, scanning systems is thermal infrared. Um, so, you've got the picture of the bat there. Um, it's a pseudo color image. That is, we've taken the various levels of, in this case, emittance of radiation from the bat. And, you might just display that as a grayscale image, but to make it look nicer and to be able to tell differences in the colors, we've displayed it so that the hottest temperatures are white and the coolest temperatures are magenta. So all objects emit radiation as a function of temperature and emissivity. Um, they constantly emit energy. We can detect thermal energy emitted during either the day or night. So we can observe objects at night if we want to. Objects that are in the temperature range commonly found on Earth, which is about 300 degrees Kelvin, or 27 degrees Celsius. They all emit energy in the 4 to 14 micrometer range. And as we discussed, because of this average temperature and the relatively low amount of solar radiation in this range can be called the thermal infrared. Any observations you make of, in this case, any observations, I should say, of light was probably emitted from an object and was not emitted by the sun and then reflected off the object. So Wien's displacement law allows us to relate the peak wavelength of maximum power that you could observe using remote sensing to the temperature. And that's just that the wavelength of maximum emission is going to be 2897 over temperature. So Earth is 300 degrees Kelvin. Therefore, that maximum wavelength of emission is about 9.7 micrometers. A forest fire, that should say, is about 1,000 degrees Kelvin, and therefore the wavelength of maximum emission is about 2.9 micrometers. And so we can actually use the further mid-infrared band on the thematic mapper to make some high temperature fire measurements. So we talk about emissivity. In remote sensing of temperature, we distinguish two types of temperatures. One is the kinetic temperature, right? That's the actual temperature taken with a thermometer if you were in the field with a thermometer. The radiant temperature is the temperature that's inferred from the radiation being emitted. And the two temperatures are related by the following equation. The radiant temperature is equal to emissivity to the quarter power times the kinetic temperature. And emissivity is just kind of a function of the type of surface we're talking about. If we're talking about what we call a black body, that would be a perfect emitter, and the emissivity would be 1. Things like water are almost perfect emitters. So a black body is an object that will absorb completely all frequency of radiation, and by extension will emit completely at all frequencies. True black bodies only exist as a theoretical abstraction. A gray body is an object that radiates with the same emissivity at all wavelengths, and for which emissivity is less than 1. So that's that dashed line in the image. The ratio between the amount of energy that's going to be emitted and the amount of energy being emitted by the black body is some ratio. A non-uniform gray body is an object that radiates with a different emissivity at different wavelengths, and that's the line with the little dots on it. And so that's the hard case, right? Because if you know that what you're looking at is a gray body, then you can pretty much just put in a single emissivity value to make the correction. If you're dealing with a gray body that's non-uniform, then you need to know the exact emissivity at a particular wavelength that you're observing at. So some factors influencing emissivity: color. Objects that are darker in the visible are usually better absorbers and emitters, i.e. they have a higher emissivity. Surface roughness. High surface roughness results in a greater surface area for absorption and re-emission of energy. Moisture content. Moisture objects have a greater ability to absorb and emit energy. So without an accurate emissivity estimates, absolute temperatures can't be determined, but relative temperatures can. And luckily, water is one substance with a constant emissivity of about 0.98. So with just a bit of a fudge factor there, that emissivity, absolute temperatures can be retrieved from water. Most thermal infrared cannot penetrate clouds, although it can penetrate smoke. And so that's vital. Excuse me. That's vital for fire applications. It's also responsible for the warming effect of clouds at night. So thermal infrared cannot penetrate clouds, so it bounces back at the Earth. There are 3 atmospheric windows in thermal, one at 2.9 to 4.1 micrometers, one at 4.5 to 5.5 micrometers, and one at 8 to 14 micrometers. Fire detection is done in the first window just because that's where you're going to be able to see the higher temperatures, and then the others are used just for general remote sensing of land surface features. One of the interesting things about thermal is you can use information about diurnal heating effects. So just as seasonal phenology increases the information available from optical imagery, diurnal patterns of heating can increase the information available from thermal images, if the interest is the heat of objects per se. However, if the interest is in the properties of objects as determined from emissivity, even heating of objects is required. So diurnal fluctuations would introduce differences in the heating of objects as a function of orientation, slope and azimuth, shadowing, etc. Therefore, many collections of thermal imagery take place at night or in the period just pre-dawn. And some applications: fire mapping, a huge application. Major fires are mapped every night so that they can get an idea of where the hot spots are going to be for the next day. Volcano monitoring. There's a list of volcanoes that are observed every day from MODIS to make sure there haven't been changes in the temperature. Geologic mapping, you can use that difference in emissivity over some landscapes to figure out whether or not you have different rock types. And then water temperature and flows, and that's a huge application, particularly for weather forecasting. So for instance, El Nino and La Nina are detected using the thermal, the temperature of surface waters in the Pacific. And here's just a picture that I like, which is the Gulf Stream along the eastern coast of the United States. And you can see the eddies where water mixes based on their different temperatures. And thermal information is so important that there was a big controversy concerning it with the design of Landsat 8. So this used to be called the Landsat Data Continuity Mission. Once it flew, it was called Landsat 8. And the whole purpose of Landsat 8 was to continue the historic timeline of Landsat. The original plans for the mission did not include a thermal band because the thermal band requires an entirely different imaging subsystem, and they were originally going to launch it and put it in private contractors' hands, and the private contractors didn't want to pay for building the system because they didn't see a market for thermal data. But it turns out that one of the applications of thermal data is for measuring evapotranspiration, right? So evapotranspiration, just the rate at which water is either evaporating from a surface or being transpired by plants. And this allows particularly Western states in the United States to operationally monitor water consumption on a field by field basis. And it uses energy balance based evapotranspiration models. So you know the temperature on the surface, you know the amount of radiation coming in, you know the leaf cover because you're getting that from NDVI, and you combine it. So for instance, the Idaho Department of Water uses thermal band imagery to manage water rights management, because if a field is cooler than the fields around it, that means it must be irrigating. When they're doing purchasing of water rights for endangered species and agreements with Native American entities, you need to be able to make sure that the people you're buying the water rights for are not also, sort of double dipping. They use it for hydrologic modeling. They use it for prediction of groundwater resources or groundwater recharge from surface irrigation, quantification of water consumption during water rights litigation to see if people are diverting more water than they're legally allowed to. Management of stream diversions for endangered species. So there's a very big project that used airborne thermal to look at temperatures of rivers in the Pacific Northwest, because the higher temperatures were leading to fish mortality. And then a range of modeling applications, such as, modeling the transition, the effect of the transition of land use from agriculture to urban land use and its effect on water consumption. And I'm sorry, I didn't finish that up. The rest of the story is that the Western Governors Association, which is what it sounds like, this, very political body that lobbies in Washington, lobbied to have the thermal band included on Landsat 8, which is kind of a wonky thing for them to be interested in, but it was considered so important that they have this technology so they could continue making these observations and doing this modeling, that they ultimately were able to get the thermal system added to Landsat 8. And I'll just leave you with this review of what we spoke about with respect to line scanners.